Welcome to a screencast on nuclear stability. One question we need to consider now is, why does nuclear decay occur at all? Well, nuclei are made up of protons, and protons are positively charged and they repel each other. So if all we had in a nucleus was protons, we wouldn't expect it to hold together at all. We'd expect the protons to fly apart due to their mutual repulsion. But nuclei, of course, contain neutrons as well, and it turns out that the neutrons act as kind of a glue to hold the nucleus together. Now this is being very simplistic. We're not going into the details of this, but here's a picture of a nucleus. We have neutrons and protons, and the protons repel each other, but neutrons attract protons and neutrons attract neutrons. That's what's holding the nucleus together. And this attraction between the closely packed protons and neutrons is what's called the nuclear strong force. So this is the thing that holds the nucleus together. Now, it's a pretty close balance between these opposing forces, the repulsion of the positive charges and the attraction between protons and neutrons in the nuclear strong force. And a couple other things to note. One is we've seen in previous chemistry, our previous chemistry experience, that sodium and other elements have what are called quantized electron energy levels. So there's a ground state for the electrons in sodium, there's an excited state, in fact there's many excited states, and these quantized energy states exist for electrons in a given atom. Well, it turns out there are quantized energy states for the protons and neutrons in the nucleus of atoms as well. Now, a couple key things to note. We'll come back to this later. Energy differences between electron energy levels are typically on the order of a few electron volts. That's what EV stands for. And nuclear energy levels, differences between those are typically in mega electron volts. That's what the MeV stands for. So maybe 1,000,000 times bigger for nuclear energy levels. So they're similar to electronic energy levels, but they're much, much higher energies, about 1,000,000 times more. Now, if we look at all of the various isotopes that exist in the world, it turns out there's a pretty broad band of isotopes that can exist, but not all of them are stable. Here is an image showing the both unstable and stable nuclei. All of these blue and red dots stand for nuclei that do exist at least somewhat. So if we have, let's say, 70 protons and 90 neutrons, we can go and find whether that isotope exists or not, and we can also find whether it's stable or not. Now the blue dots represent unstable nuclei, so these are ones that are radioactive, and the red dots represent stable nuclei. These are ones that are not radioactive. You can see there's a fairly broad band of isotopes that can exist, so that's all of the dots, the blue and the red. So it's not everything in the world that's even possible, but there's a much, much smaller number of isotopes that are not radioactive, and that's known as the zone of stability. So these red dots, those are the stable isotopes called the zone of stability. The blue dots are unstable isotopes, and above that line, the instability is typically because they have too many neutrons, and below the sort of red zone of stability are nuclei that are unstable because they have too many protons. Here's a kind of zoomed in image of part of this graph. On this graph, the non-radioactive isotopes are shown in green, so you can see how few there are relatively speaking. The blue, yellow, and sort of orangey red dots are radioactive isotopes, and depending upon whether they are above the line or not, they will be having too many neutrons or too many protons for stability. Now, a couple other things to note. if we total up all of the stable isotopes that exist and categorize them as having either even number or odd number of neutrons, and same for protons, what we see is there are very few odd number protons, odd numbered neutron isotopes that are stable, quite a few even neutrons and odd protons, quite a few even protons and odd neutrons, and then of course the most with even protons and even neutrons. So even numbers of neutrons, even numbers of protons, or both are much more likely to be a stable nuclear arrangement than if we have odd numbers of nucleons, either neutrons or protons or both. And it turns out that certain numbers of neutrons and protons are especially stable. 2 or 8 or 20 or 28 or 50 or 82 protons, and 2 or 8 or 20 or 28 or 50 or 82 or 126 neutrons are extra stable nuclei. And notice this is kind of similar to electrons, where when we have a filled shell of electrons, we have 2 in the first filled shell or 8 in the second filled shell, giving us a total of 10 electrons, or 8 more in the next filled shell, giving us a total of 18 electrons. So we have some numbers of neutrons and protons that are especially stable, just like we have numbers of electrons that are especially stable. And these numbers of protons and neutrons that are especially stable are what are called magic numbers. Now, also, if the nucleus is big enough, and big enough for us is beyond the element 82 or 83, the neutron glue isn't good enough to hold the nucleus together, and all the nuclei beyond 82 or 83 are unstable. And going back to our trends in types of nuclear decay, here is showing types of nuclear decay that occur, and this is relative to our zone of stability. Beta emission tends to occur when we have too many neutrons, not enough protons. Non-radioactive ones are in green. Positron emission or electron capture occurs if we have too many protons, and then alpha emission occurs if we have way too many protons. So here's a bit of a summary. Beyond 83, likely alpha decay. Too many neutrons, likely beta decay. Too many protons, likely alpha decay if it's really way too many protons, or electron capture, or positron emission. Now, if we were to assemble a nucleus of, let's say, oxygen, what we would do is we'd take 8 protons and 8 neutrons and put them together. Now, we know how much a proton weighs, we know how much a neutron weighs. We can add those up and see how much 8 protons plus 8 neutrons weighs. And when we compare that calculated mass of 8 protons plus 8 neutrons to the measured mass of an oxygen-16 nucleus, it turns out that the calculated mass of the individual protons and neutrons is more than the mass of an oxygen-16 nucleus. So the mass of a nucleus, this is true in general, is less than the mass of the nucleons that make it up. Now, what's going on here? Well, it turns out that this missing mass is what's called the mass defect of the nucleus, and in fact it's not really missing, it just has been turned into energy to hold the nucleus together. So let's see how big the mass defect is for oxygen-16. Okay, so if we look at a table of nuclear masses, we can look up what the mass of a neutron is, what the mass of a proton is, which is the same as the isotope hydrogen-1. Neutron is 1.00867 AMU. Hydrogen atom or proton, nucleus of a hydrogen atom or a proton is 1.00728 AMU, and oxygen-16 has a mass of 15.99052 AMU for the nucleus. So 8 times the mass of a proton plus 8 times the mass of a neutron adds up to 16.12760 AMU. We're being fairly precise here. Oxygen nucleus, 15.99052 AMU. You can see that the protons plus neutrons total is more than the mass of an oxygen-16 nucleus, so it weighs more. And if we do the difference between 16.12760 and 15.99052, we get 0.13708 AMU. So that, a little more than 1/10 of an AMU mass difference, is the mass defect for oxygen-16. Now, we've already seen that the measured mass of an oxygen-16 nucleus is less than the mass of the protons and neutrons that make it up, and that mass difference, in fact, is 0.13708 AMU. Now, to convert this mass per one atom or one nucleus to a mass per nucleon, we divide the mass difference by the number of total nuclear particles, or total nucleons, which is 16, because we have 8 protons and 8 neutrons, and that gives us 0.0085675 AMU per nucleon as the mass difference. Now note that this mass difference creates, or in a sense, some energy, or the mass difference is converted into energy via the Einstein equation, delta E equals delta mc squared. So if we now start with our mass difference per nucleon, note that this is an AMU, and units that we often like to have for energy are either joules or sometimes mega electron volts, which is what we're going to do here. So we're going to convert from AMU into kilograms, and that will give us a mass difference in kilograms. That's our delta M. We multiply it by the speed of light squared, and notice that the number we get now will be kilogram meter squared per second squared, which is joules per nucleon. And then there are 1 mega electron volt is equal to 1.609 times 10 to the minus 13th joules. So this converts from joules into mega electron volts per nucleon. And what we get for oxygen 16 is almost 8 mega electron volts per nucleon for the binding energy, 7.947. Now, if we graph mass number for various elements versus their binding energy per nucleon, if we do the kind of calculation we just did for different elements, and notice there's oxygen at about 8 mega electron volts per nucleon, this trend in binding energy per nucleon for the different elements tells us about their relative stabilities, or the relative stabilities of their nuclei. Nuclei that have less binding energy per nucleon are not as stable. Ones that have more binding energy per nucleon are more stable. So light elements can end up becoming more stable. They can go up to higher binding energies per nucleon by undergoing what's called nuclear fusion, where small nuclei fuse or stick together to make larger nuclei. And at the other end of the isotope spectrum, so to speak, heavy elements also have lower binding energy per nucleon than the peak, which is around iron 56, and so larger nuclei can also become more stable, but they do this by undergoing what's called nuclear fission, which is breaking apart into smaller nuclei. And the most stable isotope is iron 56, and the most stable isotopes are in that part of the periodic table. And that's it for the Nuclear Stability Screencast.